Hi, it's Mr. Franklin here, and this is the video key where I'm going to go over magnetism and magnetic fields, which is page 10. All magnets have two poles called north and south. Magnetic field lines always point from north to south. Like poles, likes repel, and opposites attract. That hasn't changed for magnetism, but it's actually as a result of a different phenomenon. Where are magnetic fields the strongest? Okay, the magnetic field lines are the strongest, the closest to the poles. Okay, and that's because when we see the drawings here, they're going to bunch together, and it's just going to mean that there's more strength there. Kind of like if you take a toothpick, you can break one toothpick, but if you take a whole bunch of toothpicks and put them together, they can become a lot harder to break. Okay, if a compass is free to move, which direction will it point? So it will point to geographic north, but that is the magnetic south. So a compass is basically a magnet that's allowed to spin, and the north end, which is usually the pointy end, is attracted to the south magnetic pole of the Earth. So this is, let's be clear here, this is Earth's magnetic south and Earth's geographic north. And this is one of those things where if you really try to break it down, it's all been decided by convention. We all agree that that's what it is, and so that's how we explain what it is. And mathematically, it all works out. So, number 6, draw the magnetic field lines of a bar magnet below. Here, let's get out of this text box. Number 6, draw the magnetic field lines of a bar magnet below. Remember to include the two poles and the direction of the field lines. So we've got north and south, and here's how I do it, just out of habit, because it always goes north to south. I draw my line like that, so it's just building a habit so that I don't forget. And these are not, my drawing is never beautiful, but this is a little harder. Okay, north to south. Now, this is a static drawing. If I were to look at this on paper, and I could not tell which direction those lines are pointing, so we got to put little arrows. So we're going to put arrows indicating that it's going from north to south. Now the number one mistake people make is they're drawing arrows going around, and they just keep going around. Well, that's wrong. So north to south. So I always start on the north side, and I work my way to the south, and that way, if I do it like that every time, I won't forget. And we should draw at least one arrow on the inner line. And we could draw a bunch of arrows. Here, we'll put another one. Okay? North to south, north to south. Okay? So that's how you draw the field lines. And you can notice here, if they all start from the north end, they all start to bunch up here, so the magnetic field is actually stronger here, and it's stronger closer to the magnet, and as you get further away, the field strength gets weaker. Okay. Earth's magnetic north pole is actually Earth's geographic south pole. True, we already said that. Moving charged objects. This is really cool. This is why we have electricity. Moving charged objects cause magnetic fields. And we can actually use moving magnetic fields to create moving charge, which if you've watched the induction, you've already learned about that. Okay, magnetic fields cause charged objects to move. Magnetism can produce both attractive and repulsive forces, and that is true. Draw the magnetic field lines between two magnets with like poles. So I generally always start north to south. I draw a basic setup like that, and then if I have to erase, I will erase. But this way, I'm at least oriented properly for this. Okay, So, and then the same here. So this one's north to south, north to south. Okay, so they're opposites. Well, it's basically just like drawing the regular magnet lines. But notice this is really important. They repel because these lines never connect up. Okay? So I know on the key they don't draw that half of the magnet. So that's what you see. North to south, north to south. But the important thing is they repel because these lines never actually connect together, and so they actually push apart. You can almost think of it, if I were to push this magnet this way and this magnet this way, these field lines act like a spring or a sponge or some kind of cushion where as you push it together, they push back on each other, okay? And that's because they don't connect up. If I were to draw a magnet with, let's do this one south and this one north, and let's do this magnet north and south, what's actually going to happen is now it's going to go north to south, but now it's going to connect north to south, okay? And you're going to get this north to south connection. So in a sense, what happens, it becomes a big magnet. So, which leads me into this next picture, okay? Draw the magnetic domains in a highly magnetized material. So a domain is nothing more than a magnet. It's just as small as the atomic level, okay? So think of these as a bunch of north to south magnets, north to south, north to south. Well, now they're all linked up. And so as they all link up, the magnet gets bigger and bigger, stronger and stronger, because they're all linking up. But they're all in the same direction. In chemistry, you might get into it, but this is all because of d orbital electrons. The result is you get all these little baby magnets called a domain, and they all point in the same direction, which means this becomes magnetized. Okay? Now, if you've ever messed with a bar magnet, you will also know that there are some things like iron that's not magnetized. It's a metal, but it does have atoms with d orbital electrons that are magnetic. But all the atoms, all the baby domains, all the baby magnets, if you will, are all pointing in random directions. All these baby magnets. The most important thing is they're all pointing in random directions. The more random, the less magnetized. But this is why, like a piece of magnet, you can actually strike it with a hammer, and you cause all these magnets to line up and look like this, and it becomes remagnetized. When you take a nail, an iron nail, its magnetic domains look like this, and you run an electric current through it, it actually causes, because a moving charge creates a magnetic field, this magnetic field forces all of these little magnets to turn, just like a compass, and cause them to line up, and you get a electromagnet, okay? So that is page 10, magnetism and magnetic fields.